displacement. Let's talk about relative velocity and relative acceleration. Now, what does relative velocity or relative acceleration mean? Any relative quantity means that it depends on which frame of reference we are sitting in. That is, whether we ourselves are at rest or whether we ourselves are moving, and how these laws of physics apply in the frame that we are in. Because in the end, we have to deal with problems from the perspectives which we are in. If we try to imagine any relative quantity, we should focus on that particular quantity and not the surroundings of that quantity, because they will be dealt with from a separate reference frame. So let's deal with the kinematic graphs for a particle moving with a constant velocity. Let's deal with an example of a body moving in a straight line, say from point A to point B. Imagine a ball that is rolling along the floor at your house. Let's try and plot the kinematic graphs of that particle, assuming that it's moving with a constant velocity. What will the position time graph look like? The position at time 0 is, assume, 0. After some time, say in 5 seconds, it would have moved a certain distance based on its velocity. In 10 seconds, that distance would have doubled. After all, the particle is moving with a constant speed. In 15 seconds, that distance would have tripled. Since the particle is moving with a constant speed, it will cover the same amount of distance in the same time. Therefore, the position time graph will be a straight line that is increasing, and its slope will represent the velocity. What will the velocity time graph look like? As the velocity is not changing with time, the velocity at time t is equal to 0, at time t is equal to 5, at time t is equal to 15, will all be exactly the same. In the example that we present to you, this is a little more than 10 units. What will the acceleration be? After all, acceleration is the rate of change of velocity. Since this particle is moving with the same velocity, there is no acceleration. The velocity is same throughout. Therefore, the acceleration, which would be final velocity minus initial velocity divided by the time, is 0, since the final velocity and the initial velocity at any two instances is exactly the same. So the acceleration graph will be a straight line with the acceleration equal to 0. There could of course be changes in this graph depending on how the body moves. Suppose we were to plot the displacement graph of this particle, and the particle was moving forward and then coming back. In which case the displacement of course would be 0, the distance would be non-zero. What if this particle was not moving with a constant velocity? Imagine for an instance that it was moving with a constant acceleration. In that case, the position time graph would look like a curve, whereas the velocity time graph would be a straight line, since uniform acceleration means that the velocity is increasing linearly with time. What if the acceleration itself was changing? In that case, the position time graph, having moved from linear to quadratic, would now become more complicated. The velocity time graph would also increase its degree. It would no longer be a straight line, it would also be a curve. If the acceleration was increasing linearly, then the acceleration time graph would be a straight line at this point. Let's take an interesting example. If you were playing cricket and hitting the ball and trying to measure with what speed you've hit the ball and at what angle, and you applied the laws of motion and kinematics to that particular situation, you would find that the distance that your ball has actually moved is considerably less than what you would have predicted. The reason for this is that in the kinematical problems that we deal with, by and large in the JEE, we assume that the only force present is gravity. That is, gravity is pulling the balls towards the earth. That's not true. If you've ever seen a feather falling down, you know that the air itself has a particular force. This force is called air drag. So look at your screens and look at the trajectories of two particles which are thrown with the same initial velocity and the same angle. In the situations that we deal with, where only gravity is present, the shape is a perfect parabola and the distance is considerably more. However, if we take into account real life situations where air drag is present, that air drag tends to oppose the motion of the body. The force is essentially minus kV, that is, it opposes the velocity. In this case, what that means is that the particle will stop considerably sooner. The shape will actually be a bit more complicated, We'll deal with that in later chapters. Imagine a projectile that is thrown horizontally from a cliff. When we say throw horizontally, we mean that it is thrown with a velocity in only the horizontal direction. Remember, the only thing that changes and affects this motion is a force. That force in this case is gravity. That force decides the acceleration, which changes the velocity. Let's try and analyze the motion of this particle using the concept of vectors. At every instant, the projectile has two velocities, a horizontal velocity and a vertical velocity. Let the horizontal velocity vector be Vx, the vertical velocity vector be Vy. Since we are ignoring air drag, there is no force in the horizontal direction. Therefore, there is no acceleration and the horizontal velocity will remain constant. However, in the vertical direction, initially though the velocity was zero, a force of gravity is acting that tends to pull the body downwards. As this force is causing an acceleration, the vertical velocity will keep increasing. Assume that the force of gravity causes an acceleration of 10 meters per second, then as the time increases, the velocity in the vertical direction also increases. In 1 second, it will be 10 meters per second, in 5 seconds, 50, in 9 seconds, 90 meters per second, and so on. This is what causes the action that you see, the motion of a parabola. How do you solve problems in kinematics? In questions which involve multiple speeds, suppose you have a boat in a stream, you have to take into account the speed of the stream, the speed of the wind. We have to understand the effects of these forces of the stream and the wind on the particular body that we are studying. So for instance, suppose that you have a motorized ship which is moving in a river. The wind is blowing above it with a particular velocity. In that case, the velocity of the river will affect the body that is in it. So the motorized ship's velocity will be a resultant of the original velocity of the ship, which is generated by the motor, and the velocity of the river. It will be the vector addition of these two. The wind, of course, will have no effect. However, if a plane is moving in the air, then the speed of the wind affects the speed of the plane. The speed of the plane will be the vector addition of the velocity of the plane as generated by its engine and the velocity of the wind. We must take care to take into account all the factors that are influencing that body's velocity. Consider questions where you have projectiles. Over here, it's very important to use the concept of vectors accurately and conveniently. One of the convenient ways of doing this is to split the motion along perpendicular axes. Generally, these are horizontal and vertical. However, we may find other axes that are convenient. Keep in mind always that we assume the gravitational field is perfectly vertical. Therefore, the equation that we derive for motion of a body is a parabola. However, the actual path is elliptical, and we will study this later in gravitation. Be clear on how to generate the Vt, St, Xt and acceleration time graphs, along with what their slopes mean, etc. Now,